So there are a lot of tools out there that are just really short programs written in C designed to serve one particular purpose, like compressing or extracting some proprietary archive format. And usually what ends up happening, especially in, say, like the Wii hacking or modding scene, is that people pass around Windows binaries of these C programs that were built against something like Cygwin, and so they need to give you like the whole Cygwin DLL and whatever other dependencies it requires in addition to the program. And while that does work, it seems a little bit messy, and you're never quite sure what to do in the case of like a conflict, or you don't really know which DLLs belong to which program. Anyway, what I'm going to do here is show you in two steps really how I take this simple C program. Its only dependency is zlib for deflate compression and extraction. I'll turn the C program into a C++ CLI program that has no external dependencies, just the Visual C++ redistributable and .NET Framework 4.7.2, which I think both come with Windows, and I think they have for the last couple of years at least. This is kind of an odd use of C++ CLI, but I think it has some potential to help people out if they are .NET developers who don't really understand C all that well. So let's take a look at the code of this program. I've modified it a little because I've actually already done all these things in the source code repository that I posted my fork in, but I wanted to show you what you can do and the steps to do it. The first step is to take this program and change it from C into a program that can also compile, if you want, as C++. And for small programs like this, where it's like one file, it's usually not a whole lot of effort. I've got a Linux virtual machine here that I'm going to use. Now I'll compile the program. And if I run a.out, you see it's been compiled. I made an example CCF archive earlier so you can see the extraction in action. So if you pull open this file, you see these 4 JPEGs got extracted, and yeah, they're JPEGs. That's what they are. Anyway, so like I said, our first step is to make sure this program can also compile as a C++ program. And if I bring open this console window, you see the problems we have. And there aren't really that many, if you think about it. The kinds of problems that I usually see when I take a C source file and make it work with C++ is one of two things. First, the malloc returns a void pointer, which in C you can just implicitly cast to any type of pointer. In C++ you need to do that cast explicitly. So file entries is defined here. It's a pointer to a CCF file struct. And then we've got it being allocated again down here. This is the the pointer inside the pointer. So it's really a list to pointers to these structures is what's going on. Line 92, we've got something similar, data buffer here, character pointer. So either like equivalent to a byte array or a string in a managed.NET app. File buffer is the same way. Basically, they're both just storing data read in or written out to files. And then you see line 101, and there's actually 3 errors on this line, and that's because the uncompressed function, which is part of zlib, first of all, it doesn't expect character pointer, it expects unsigned character. So unsigned 8-bit integer instead of a signed one is what it means. So I'll change file buffer and data buffer to match, And then the size variable, instead of a long, it needs to be an unsigned long. And now you can see the program compiled. If we jump back here, you should see our beautiful JPEGs. So we've got it working as C++ now, and we can see it also will still compile as regular C as well successfully. So I'm going to create this project, probably easiest to start out by putting it in a new folder. Find CLR empty project, and you can choose either .NET Framework or .NET Core depending on what fits your needs. .NET Core is probably going to be the better choice going forward. That's where the new features are going to arrive. But in this case, I know .NET Framework 4.7 works, and it's already installed on people's computers. But yeah, you can make your own decision about that. I'll call this project, and solution will be called, let's just do the extractor for the purposes of this video. So I'll call it ccfx-net or -.net or something. I'll put it in my desktop. And then, yeah, I'll put the project and the solution file in the same folder. So there are, now that this is here, I've created it, I'm just going to go ahead and move that back into the same folder as my other things, kind of merge them together, and then open it again. So we need to add our source files, and in this case we're lucky that there is only one source file. I can go to Add Existing Item and pick out ccfx. I don't want all those files to be committed. I need a get ignore file. So not a new project. I want to add a new solution item. I'll call it .getIgnore. Oh, I forgot there is one. Let me add it as a solution item just so I don't forget again. Let's say we don't want any CCF files to be accidentally committed to the repository. We don't want the Visual Studio kind of cache area. We don't want the user settings file. But yeah, everything else. Oh, we also don't want the builds to be committed. That should take care of that. Now on to getting the application to build. Step one is we need to configure a few more properties in this dialog in the project settings. Under C/C++, go to Advanced, and C++ CLI is called that for a reason. It's not C CLI. So we're going to compile everything in the project to C++ and not as C. And then, so let's jump back here and see what we've got now. So if we look at the file now, what Visual Studio says about it. Obviously, we're not including zlib in this project, but I should say as long as we're compiling it as C++ CLI, we can do this and still keep the source code's ability to be compiled and run in the original way. So I just find an ifdef C++ CLI, then I want to do some other stuff besides zlib, but if it's not, we do want zlib. And I'm just, to make it a little easier, I'm going to go ahead and list out the namespaces we're going to use. This is, a variant of C++, so you could just as easily put individual class names up here. And it might actually be good practice once we're done here to go ahead and replace these with actually just the individual classes that we're using so you don't run into conflicts. We know we need system. We need system.io. We're also going to need something called DeflateStream in system.compression, which is in the system assembly, which is not included by default from this template. Maybe a little surprisingly, but we can add it. And now we should have the system.io compression namespace. So let's go down to the actual code. We're going to need to match what the uncompressed function does. Now, the first variable is going to be the destination pointer. Second variable is input/output of destination size. Now, it might come back smaller. That's what's kind of unique about this function is this is both an input variable and an output variable. It just so happens that the CCF format is declaring upfront what the actual uncompressed size could be. And just to simplify things, we're going to take it at its word. We're not going to try to deal with that. That would be a good idea for future improvement. But we've got the two other arguments, which are the pointer it should write out to, and then the pretty much the capacity, the number of bytes available to write out to. So with that, we want to block this whole part off, do something completely different if we're using C++ CLI. But if we're not, then go ahead and keep using zlib. So now it's time to write our code. So there's no direct equivalent to the uncompressed zlib function.net. It's really split up into three. The format, the output input format of these compressed and uncompressed functions, split up into three parts. There's the header, which is 2 bytes just to identify the type of data. First byte is 78, second byte is 9C. Then we've got the actual compressed data, and then finally 32-bit checksum that is stored big endian, and we'll need to check that. So first thing we want to check is first 2 bytes in data buffer. First one, if it's not 78, or if we then check the second one and it's not 9C, then we quit out with an error, something like the compressed data is corrupted. Sure. And next, now it comes time to actually do the decompressing of the data. The deflate algorithm is something that's available in .NET. .NET, I think, starting in 4.5, it actually just uses zlib under the hood. Starting in .NET 5 actually fixes some bugs, but we can work around that. I'll show you when I get to it. But first I want to show you something I think is really cool and something that could be useful not just in C++ CLI programming, but in a C# app where you're dealing directly with native pointers. Here's a variant of the stream class. First of all, that means it's a handle, and this is how you generally refer to reference types, to .NET reference types in C++ CLI. You're saying this is not something on the stack, this is not a value type, it is a ref class, and I need to use this, which is like, C and C++ have the pointer, the little star. This is kind of designed to resemble that in its semantics. We're making a variable where the type is stream. It's a handle to something that's garbage collected, and we're going to call input stream. Because it's a garbage collected .NET thing, keyword to use is not new, it's GC new is our keyword. And the type we're going to use is called UnmanagedMemoryStream. Now this is very cool. It lets you, the constructor we're going to use takes 4 arguments. First is a byte pointer, the place we want to either read from or write to. And for us, that is going to be 2 bytes into data buffer. So we'll do data buffer plus 2 elements, which is 2 bytes in this case. Second, let's go back to the right constructor. This is going to be the length, which is right here. But we want to subtract 2 bytes for the header, which we already skipped, and subtract 4 bytes at the end for the checksum. The capacity is going to be the same as the length. Split this out, just make it a little more readable. And then finally, our last argument, we need to say, do we want to read from this? Do we want to write to it? Do we want to do both? this we want to read from. So there you go. It's a way to access unmanaged memory as a .NET stream. And you'll see why we want to use a stream when we do the decompression. So we'll make a similar output stream. This will go right into file buffer. We've already got the length here, and like I said, just to save time in this example, we're assuming it's correct. And that's not going to change as a result of the decompression. This is something we want to write to. Now, to perform the actual decompression, there's another type of stream. We're going to call it decompressor. And this type is called DeflateStream. And this is in the system.io.compression namespace. So its argument is the stream that it's wrapping, which for us is going to be input stream. And then our compression mode is going to be decompress. That's the constructor that we'll use. So let's simply perform the actual decompression by reading everything from that decompressor stream wrapper on the input stream and copying it to the output stream. And then to make sure it's complete, because apparently .flush doesn't work right on a deflate stream in .NET 4.x, we can work around that by actually just straight up closing the stream. By the way, at the end I'll show you a neat little trick in C++ CLI that can either make your code more readable or a complete mess, but ultimately it's a way to do something similar to C# or Visual Basic or F# using statements. But let's continue for now. The last step is to verify the checksum. And unfortunately, the Adler32 checksum used in this algorithm is not something that .NET exposes, but luckily it's a very simple algorithm. We can just write our own implementation. We'll have two counts, A is 1 and B is 0, and then we'll loop through each byte in the output data, the uncompressed data, in order to generate the checksum. So let's just say starting at index 0, going until size, and then adding 1 each time. We'll get the current byte, we'll store in a variable called x. And what we're doing here is file buffer is where we store the uncompressed data, index into it, get the right byte. Okay, so for A, the new value of A is first add that byte to A, and then take the remainder after dividing by 65,521. For B, we take B, we add A, and then take the remainder after dividing by 65,521. So I've got those two numbers. Ultimately, the checksum is going to be B in the high 2 bytes, and then A in the low 2 bytes. Now, this checksum is the last 4 bytes of the compressed data, but it is stored big endian, and like I said, I think I said earlier, the assumption is that this code is going to be running on a little endian machine. Of course, it has to be able to run on a little endian machine. That's like every x86 and ARM processor. So we're just going to, instead of bringing in like in to hs, h to ns, h to nl, those functions, we're just going to check each byte individually. First, though, I want a pointer to the checksum location, just to make this a little bit easier. Location of the checksum is data buffer plus, let's go to the end of that data buffer, but then back up 4 bytes because that's where the checksum is. So then we can check whether all 4 bytes match one by one. The first byte, blank out everything except that top byte, 2, 3, 4, 5, 6, there we go. Move it over into the lowest byte, and then compare to that first byte of the checksum. The other 3 bytes are going to look pretty similar, except this goes 1, 2, 3. This goes 8, 16, 8, 0, and then for this, of course, we need to move over what byte we're actually keeping instead of blinking out. That Boolean will tell us, by the way, Boolean being, I think, a C++ thing, but this code is only going to be compiled if we're compiling a C++, so we're all right. And now, if the checksum doesn't match, we just print out a message. Maybe Adler32 checksum does not match. And then we can say expected that number in hex actual 4 bytes, just because that's what we have. Hopefully we won't have to hit this statement, but if we do, it'll provide us a little more information. So I'll press F6 on my keyboard to compile it. So before I go any further, there were, you might have noticed 2 problems in my code. So the first one that I noticed before doing editing, those should be equal signs, obviously. And the second, here we're comparing data buffer plus file size. That should be data buffer plus data size. So this should be data size here, there should be data size here, there should be data size here, because file size is used there. So now that we've got that all the way, I'll hit F6, that should build the project, and then I will navigate into a command line to the folder where the executable file ended up. It's called the same name as the project as the default. So it's that. Go backwards with my backslashes to demo.ccf, backslashes because this is it's not Cygwin, it's a natively compiled Windows application with Visual Studio. And so those, after fixing those 2 obvious errors, I was able to get the program running correctly. JPEG, 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 JPEG. It successfully extracted the CCF archive, and if you look in here, and I'll even just show you by copying this to completely empty folder on my desktop, and then going there. But my point is, no other DLLs. There's no zlib, there's no Cygwin, there's no like C++ redistributable that I have in here. It's using the C++ library and the .NET library that are installed in Windows, which means I can just extract the JPEGs, no DLLs needed. This file is under 100 kilobytes. It is 71.5 kilobytes, and that's it. Of course, we've done that by requiring a dependency on .NET, which is, of course, a huge monolith, but it's a huge monolith that, let's be honest, if you're targeting Windows, if you're distributing a Windows binary, chances are people already have that installed. Maybe that wasn't true, 12 years ago when, or whenever this code was written, but it's pretty much true now. And are there better ways to compile C on Windows? Could you use MSys? Yeah, of course you could use MSys, and you probably should, but the fact is I'm a .NET programmer. I didn't feel like learning how. I'd rather do something cool and kind of crazy like this. So I said earlier I was going to show you an equivalent to the using statement. So this will be the last part of it. In C++ for native C or C++ types, for those value types, you can have them on the stack, or you can have a pointer to them. You can have char a equals 4, or you can have a pointer, pointer to char b. It's the address of a, right? So there is something similar you can do with handles. You've got your input stream, you've got your output stream, those are handles. But what I could do, I could allocate them as if it was a C++ class that I was allocating on the stack, and kind of pretend that's on the stack, and C++ is like, wink, wink, yeah, I know it's not really on the stack, but I'm going to treat it like it is. And here's what the syntax for that looks like. Obviously, you need the actual class name here, but type is just UnmanagedMemoryStream, and it looks like that. And now this is not a handle. This is just an unmanaged memory stream being on the stack. Not really, but acting like it is. We can do the same thing for output stream. Looks like that. You'll notice here, there's a problem here. What's the problem? Kind of hard to tell. But it says the arguments don't match. Well, here's what you need to do. So this is a .NET method. It wants a reference type. Of course, what it's going to expect is a handle, because this weird stack thing is just C++ CLI. Other .NET languages don't have that. It wants a handle, right? How do you get a handle? You use this operator, a %sign. It's literally, there's a %sign, and that's how you get the handle of something that's stack allocated. And you're like, where did this % come from? There's just suddenly a % in my code. And I mean, there's already a caret in your code. You kind of gave up your code looking normal at that point. But you know, we can do this for the decompressor as well. We can have that allocated just on the stack like that. And then instead of these, you know, dereferencing function things, whatever they're called, the arrows, just use dots. This, of course, also needs to be a handle. But so here's a reason you might actually want to do this. When this goes out of scope, it's going to get disposed. It's going to call the .NET dispose method. And I actually don't remember if it's the dispose method or the finalizer, but I know the dispose method eventually gets called either way in this with streams. So we want the streams to only be in scope as long as we're using them, right? And that means we do not need to close the decompressor. It's going to be closed when it gets disposed, when it goes out of scope right here. And this is actually putting it in a block like this, a block that otherwise doesn't do anything except take some variables out of scope. Might look silly in like C++, but in or in C#, but in F#, where there's a use statement, which does something honestly kind of similar to this with streams. I have done this. I've made blocks that look like do something async, and then there is like a use stream in there because I want that stream to go out of scope and get closed once that block's done, right? So same kind of idea. I'll build this. Let's just make sure it actually still runs, actually still does the same thing. Of course, it goes to 64/debug. And there's the output executable right there. I run it. I'll go back to that folder where it lives. Actually, the easiest way to do that, explorer space dot. Yep, there are my JPEGs. And yes, it is working. So we have replaced zlib with a kind of weird, but ultimately kind of cool way of calling .NET. We've got, you know, part 1, part 2, and then part 3. And of course, this could be cleaned up a little if you already have a function to convert little endian to big endian to make sure that's right. But the nice thing is this code, you'll see, I kept all the original code in there hidden behind ifdefs, which means I can just run GCC again, it compiles, I can run a.out, I can do let's just delete the JPEGs. I can go back up here and do the a.out on the demo.ccf, and it gives me those JPEGs. And that's the original code running, which is still in the same file. So that's all I got. It's a pretty odd use of C++ CLI. Then again, any use of C++ CLI is going to be kind of odd because it is a weird language that you shouldn't use for normal things. But if you just want to get something in C compiling, but in a way that you don't have to deal with linking libraries, you don't have to deal with DLLs, basically you're using .NET standard library to replace whatever dependencies it has. And in that case, it might actually turn out pretty convenient to use C++ CLI like this. So yeah, that's all I got. Hope you liked it. Hope you weren't too distracted by me making obvious mistakes like this. And I'll see you next time.